So if you type, like, the number 120,000 into a standard Western computer system, the machine figures out its value based almost entirely on where the digits are placed.
Right, the position of the numbers.
Exactly. I mean, a 1 followed by 5 zeros means 120,000. It's completely positional.
Yeah, that's just the baseline Arabic numeral system we're all used to.
But if you feed that exact same computer system the Chinese equivalent of that number, so the character Shir1, that whole foundational logic of positional math just totally falls apart.
It really does. It forces the machine to completely abandon that baseline system it was designed around.
And adopt an entirely different cognitive model, which is wild. You know, we usually think of software internationalization as just like swapping out vocabulary words in a translation file.
Just updating a text document, basically.
Right. But today, we are looking at a scenario where the target language fundamentally alters the mathematical laws of how the software parses numbers. Welcome to today's deep dive, by the way.
Glad to be here for this one.
We've got some fascinating source material today. It's a highly detailed developer diary entry, specifically Notes on Haskell Programming, Part 175, written by a programmer named Ang. It was published on July 1st, 2026.
And at first glance, I mean, this is a pretty technical note.
Yeah, it looks super niche. Ang is upgrading a console application called TXT2TBook. But beneath the surface, it's really a masterclass in how different cultures fundamentally conceptualize math.
And how software engineers have to build these clever little bridges between those different systems of thought.
Exactly. So Ang is migrating this code base from Python over to Haskell. And they mentioned using AI to help refine the code.
Which is a huge contextual detail, honestly. I mean, Python is an imperative language, right? You're giving the computer a very specific step-by-step list of instructions.
Do this, then do that.
Right. But Haskell is a functional programming language. You aren't just writing instructions. You are defining what things inherently are through, well, mathematical functions.
So it's not just a copy-paste translation job.
Oh, not at all. You have to tear down the entire architectural paradigm of the app and rebuild it from scratch. AI is great for translating the raw syntax across that divide, but the human actually has to architect the logic.
Okay, let's unpack this. Before we get into the complex math, we have to understand the actual problem Ang is trying to solve.
Right, the visual output.
Yeah, formatting Chinese chapter headers for this ebook app. Ang wants to take a header containing a Chinese number, like, say, san for 3 and bai for 100.
Meaning 300, yeah.
Right. And they want to convert that text into a raw integer and then output that number using full-width numeric digits.
Which is super important for the layout.
Yeah, it's like upgrading from a standard typewriter to an architectural drafting pen, you know. Giving those numbers a wider, more dramatic footprint to match the typography. So instead of a skinny 300 squeezed on the screen, it outputs a wide green.
Yeah, because in typography, especially for Chinese and Japanese text, characters are designed to sit in a very strict, uniform grid.
Every character gets the same square footage.
Exactly. If you drop standard Western ASCII numbers into that grid, their widths vary. A standard one takes up, like, a tiny fraction of the horizontal space of a full Chinese character.
It just looks wrong.
It disrupts the visual flow completely.
Yeah.
So by converting them to full-width characters, Ang is ensuring the alignment stays structurally flawless.
But to do this, Ang starts by building this really explicit manual mapping table, a function called to full-width char.
It's very straightforward.
Yeah, it literally maps a standard 0 to a wider 0, a 1 to a wider 1, and passes other characters through. But Ang actually admits in the diary that there are much more concise ways to do this in Haskell.
Yes, they do.
So why would a programmer choose this manual, hard-coded mapping when they're using such a sophisticated language?
This raises an important question about managing a complex migration. When you move logic into a functional environment like Haskell, your initial enemy is abstraction. Well, if you use a highly abstracted formula to shift the character encodings, you're introducing a potential point of failure. And if something breaks downstream, it's a nightmare to debug.
I see.
By just writing out that 0 equals 0, Ang is basically securing the perimeter. Any developer or even an AI assistant can read that table and know with absolute certainty what the baseline is doing.
You establish the foundation before you build the penthouse.
Exactly. You can always refactor it later. The immediate goal is just architectural stability.
But, I mean, text in the real world is incredibly messy, right? A chapter header might be a preface with no numbers at all.
Oh, absolutely.
Or it might already have full-width numbers from a previous format pass.
Yeah.
If you just shove that raw text blindly into a mapping function, the app is going to crash.
It needs a dispatcher.
Right. And Ang builds this dispatcher using Haskell guards, which to me are like a hyper-intelligent bouncer at a club.
I like that analogy.
Yeah, like the bouncer doesn't just check your ID. They evaluate this complex set of rules instantly and decide exactly which room to send you to.
That's a great way to picture it. In an imperative language, you typically use nested if-else statements for this.
Which is so tedious. I always picture traditional if-else setups like toll booths on a highway.
Stop, check, go.
Exactly. The text has to pull up, stop, answer a question. Are you empty? If no, drive to the next booth. Are you a single digit? It's so mechanical.
And it slows down the visual readability of the code massively because you're layering logic inside of logic.
So how do Haskell guards fix that? How do they prevent that dreaded alphabet soup issue?
Well, the guards, which are represented by a vertical pipe symbol in the code, they function more like a modern train switch track.
Oh, I see.
The data comes down the line, and the guards evaluate all the possible conditions simultaneously. The track seamlessly shifts and routes the data without that stop-and-go clutter.
And Ang sets up 4 specific tracks here. If it's empty, it returns a null value called nothing.
Right, track 1.
Track 2, single width digits go to the mapping table. Track 3, already full width text just passes through.
And track 4 is the complex parsing engine for Chinese numerals.
Right. And Ang loves this setup.
Yeah.
In Elixir, you'd need all these different pattern matches across different functions. Here, it's all in one place.
It centralizes the decision-making perfectly.
But Ang does mention that alphabet soup problem. Like, if you pack too much Boolean logic into these guards, it gets unreadable.
Yeah, but they solve that by using a where block at the bottom of the function.
Which does what exactly?
It acts as the control tower for that train switch track. It separates the what from the how. The main guard statements stay pristine and read almost like plain English.
If empty, do X.
Exactly. The messy Boolean logic that actually calculates how to know if a string is empty is pushed down into the where block out of sight.
That's so elegant. It routes the text, and it fails gracefully by returning nothing if there are no numbers.
It keeps the compiler from crashing.
Okay, but let's follow the data down that 4th track, the Chinese numerals, because here is where it gets really interesting. This is where Western programming collides with Eastern math.
What's fascinating here is how the parsing logic has to change completely.
Because Arabic numerals use a positional place value system. Like if I see a 3, its value is dictated strictly by its column.
Right. If it's third from the right, it's 300. But Chinese numerals use a positional multiplier system.
Meaning the position alone doesn't tell you the value.
Exactly. Specific characters embedded directly in the text act as mathematical operators. You are literally searching the string for hidden multipliers.
And to process this, the code uses a function called fold left prime. Ang describes it as a finite state machine that reads the text strictly from left to right.
Character by character.
Right. The base digits range from ling for 0 up to ju for 9, but then you have positional multipliers like she for 10, bai for 100, and quin for 1000.
So it's not just dropping numbers into columns.
No, it's like the text is literally writing out an algebra equation as you read it. Ang traces the number 33 as an example. Exactly. 3, 10, 3. So the fold function uses this thing called an accumulator to hold the running state, right?
Yes, it starts at 0, it reads san, parses a 3, and stores it in the accumulator.
Then it hits the sheet.
The state machine sees sheet as an instruction to multiply by 10, so it takes the 3, multiplies it, and updates the accumulator to 30.
And then it sees the final san and just adds it, getting 33. It's computing on the fly.
It's brilliant because it doesn't force the text into Western columns. It applies transformations the second it hits an operator.
But wait, I have some pushback on this fold loop. It seems so rigid. If it encounters one single bad character, it pulls the plug on the whole operation and returns nothing.
It fails immediately, yeah.
Why wouldn't it just drop the bad character and try to salvage the rest of the numbers?
Yeah.
Like autocorrect.
It feels counterintuitive, I know, but you have to consider what this app is actually doing. It's generating an eBooks table of contents.
Right, the TOC.
If the state machine skips a character it doesn't understand, say a bai, which is a multiplier of 100, it permanently corrupts the mathematical state.
Oh, wow. I didn't think about that.
Yeah, a chapter that should be number 3200 could end up being logged as chapter 32.
Because it just appended a 2 instead of multiplying by 100? That is a massive error.
The cascading math errors would be disastrous. By enforcing strict failure, Ang guarantees a corrupted string just results in a blank entry.
which a human editor can easily spot and fix during proofreading.
Exactly. A wildly incorrect calculation hiding in the document structure is a nightmare to untangle. Strict failure is a safety net.
Okay, that makes total sense. So the state machine handles these basic positional multipliers up to the thousands perfectly. But what happens when the numbers get massive?
Well, the rules of the linguistic math change all over again.
Enter the magnitude multipliers, like 1 for 10,000 and y for 100,000.
And these do not behave like the smaller multipliers we just talked about.
Right. A basic multiplier, like 100, just applies to the immediate digit right before it. But these magnitude multipliers apply to the entire sum that preceded them.
They apply retroactively.
So if we trace 120,000, which is she or 1, it starts with she for 10. So the accumulator holds a 10.
Then it hits for 2, adding it to make 12.
And then it hits 1 for 10,000. Does this mean the program essentially has to, hold its breath?
What do you mean?
Keep a running total of 12 in its memory, grouping it together before finally hitting that magnitude multiplier to release the massive calculation all at once?
That is exactly what it does. It takes the entire accumulated state of 12 and multiplies the whole thing by 10,000.
Bringing it to 120,000? That is incredible.
And what's really amazing is that this full state machine perfectly mirrors the human cognitive process of reading large Chinese numbers.
Like human working memory.
Exactly. When a native reader processes sheer 1, they parse the 10 and the 2, conceptualize the 12, hold it in their working memory, and then scale the whole concept up by 10,000.
So Ang's code isn't just a parlor trick. It's a mathematical model that mimics human linguistic structure.
It seamlessly scales from immediate small multiplications all the way up to these massive retroactive magnitude shifts.
Because it follows the exact same logical path as the language itself.
Precisely.
So what does this all mean? We started out looking at some notes on a compiler syntax migration. But this really shows that coding isn't just typing commands into a machine.
Not at all.
It's about translating human culture, history, and linguistic logic into a format a computer can actually execute.
Right.
Ang had to teach the computer an entire culture's mathematical philosophy just to get a perfectly aligned chapter header in an ebook.
The invisible labor there is just staggering.
It really makes you appreciate the invisible, elegant math running behind the scenes the next time you scroll through an automated table of contents.
And if we connect this to the bigger picture, it leaves us with a really profound thought.
Lay it on me.
Our foundational programming languages, the operating systems, the compilers, they were built almost entirely around Western positional place value logic.
Right, the Arabic column.
But if understanding the positional multiplier logic of Chinese numerals required Ang to build this highly specialized custom state machine, it really begs the question.
What entirely new ways of writing code are out there?
Exactly. What hyper-efficient paradigms of computing might be hiding within the grammatical rules and mathematical systems of non-Western languages, just waiting to be translated into software?
An entire architecture built natively around magnitude shifts instead of sequential loops. That is something to think about. Thank you for joining us on this deep dive today and exploring the linguistic math hidden inside the machine.
Thanks for having me.
We'll see you on the next one.